Hello, my name is Dong Hwi Seo. I'm a postdoctoral researcher in Hanyang University. Firstly, I would like to express thanks to Hoju Lee for providing an opportunity to give a talk in Geometric Analysis, Past, Present, and Future Season 1. This talk, I'm going to talk about some uniqueness theorems about free boundary minimal annuli in a ball and a half ball. This talk is based on my recent paper. Now let's start with the definitions of free boundary minimal surface in a ball. We consider some manifold in n-dimensional Euclidean ball, and on one parameter family of this surface whose boundary is free to move in the boundary of the ball. Then we can take the first variation of area functional, and it consists of two integrals. First integral is taken in the interior, and the integrand is minus inner product with mean curvature and the variational vector field. And also the second integral is taken in the boundary of the surface, and the integrand is the outward unit conformal vector and the variational field. And then if we consider the critical point of the area functional, we call it as free boundary minimal sum manifold in Euclidean ball. So to be critical point, then here the mean curvature should be 0, and also the outward unit conformal vectors are perpendicular to the surface, the boundary of the sphere. So we can consider this the first definition. Here, the sigma should be minimal, and sigma meets the boundary of the ball orthogonally along its boundary. So if you consider coordinate functions defined in the surface sigma, then the minimality implies that the coordinate functions are harmonic in the interior. And also the boundary condition implies that the normal derivative of the coordinate function should be equal to the coordinate function on the boundary. So there are two basic examples of free boundary minimal surface in a ball. The first one is equatorial disk. The equatorial disk is the intersection of a ball and a plane passing through the origin. In this talk, we call those plane by a coordinate plane. And second example is critical catenoid. It is a part of the catenoid, and it is maximally stable part of the catenoid. And also it has reflection symmetry with respect to 3 coordinate planes. And there are many other examples of free boundary minimal surface in a ball, but in this talk we will concentrate on those two basic examples. Actually, this topic was initially studied by Nietzsche in 1980s. He showed that the equatorial disk is the only immersed free boundary minimal disk in three-dimensional Euclidean ball. And then in the same paper, he wrote that an embedded free boundary minimal annulus in three-dimensional ball is critical catenoid. It is still open, and it is well known by Fraser and Lee's paper. Free boundary minimal surface in a ball has an interesting relation with Steklov eigenvalue problem. This relation is observed by Fraser and Shane in 2010s, and so it has been paid attention increasingly nowadays. So let me introduce Steklov eigenvalue problem. If you consider ambient manifold M and smooth bounded domain omega, then Steklov eigenvalue problem is finding a real number sigma and smooth function defined in omega such that the function is harmonic in the interior and the normal derivative of u with respect to the outward uniqueness vector is proportional to u on the boundary. Actually, it is an eigenvalue problem, so it has discrete eigenvalues and it diverges to infinity. Also, if you consider constant function, then it is harmonic in the interior, and the normal derivative of constant function should be 0. So constant function is Steklov eigenfunction with eigenvalue 0. And then we can obtain other eigenvalues by variational characterizations. So if we consider test function as smooth function defined, a non-zero smooth function defined in the boundary, which is perpendicular to the previous eigenfunctions here. And then among these test function, we take infimum of the value of Rayleigh quotient. And the Rayleigh quotient is the L2 the square of L2 norm of the gradient of the harmonic extension of F normalized by the square of L2 norm of the function in the boundary. So the first eigenfunction should be satisfies that integral over the boundary should be 0. So if you consider Steklov eigenvalue problem defined in free boundary minimal surface in a ball, then by the definition, our coordinate function becomes the Steklov eigenfunction with eigenvalue 1. So the coordinate function should be Steklov eigenfunction, and the first eigenvalue should be less than or equal to 1. So if you assume the first eigenvalue is less than 1, then the first eigenfunction should be perpendicular to constant function and coordinate functions. Using this relation, researchers has obtained several uniqueness theorem for free boundary minimal annulus in Euclidean ball. In 2016, Fraser and Shane showed that if an immersed free boundary minimal annulus in n-dimensional Euclidean ball has the first stack-level eigenvalue 1, then it is congruent to the critical catenoid. Using this result, researchers have obtained several uniqueness theorem by imposing symmetry condition on the surface. So McGrath showed that if an embedded free boundary minimal annulus in three-dimensional Euclidean ball is invariant under the reflections of the three coordinate planes, then it should be congruent to the critical catenoid. And then Kostner and McGrath showed that if the surface has antipodal symmetry, then it should be congruent to the critical catenoid. On the other side, Barbosa and Silva considered the uniqueness theorem by imposing symmetry condition on the boundary. So they show that if the boundary of the free boundary minimal annulus is invariant under the reflections of the three coordinate planes, then it should be congruent to the critical catenoid. Now let me introduce some of my uniqueness results for critical catenoid. The first theorem says if the surface is invariant under the reflection through two coordinate planes, then it should be congruent to the critical catenoid. Actually, the number of reflection coordinate planes is reduced by 1 compared to the previous result. And also we can reduce one more reflection coordinate plane if a given reflection coordinate plane does not meet the boundary. And this problem can be considered as free boundary minimal surface in the half ball. So the second theorem says if you have an embedded free boundary minimal annulus in the half ball, and if one boundary component lies in the open hemisphere and the other boundary component lies in the equatorial disk, then this minimal annulus should be the half of the critical catenoid. So the strategy of the proof is by assuming the first eigenvalue is less than 1 and obtain a contradiction. Then by work of Fraser and Shane, we can prove that the surface should be congruent to the critical catenoid. So how to obtain a contradiction? Now we briefly review previous approach, and let me introduce my approach. To do that, first we define a nodal domain of stack-level eigenfunction. Nodal set of stack-level eigenfunction is the point of zero set of the stack-level eigenfunction, and also the nodal domain of the eigenfunction is a component of the complement of the nodal set. And Courant nodal domain theorem says if we have nth stack-level eigenfunction, then we have at most n+1 nodal domains. So for the first Steklov eigenfunction, we have at most 2 nodal domains. However, the first Steklov eigenfunction is perpendicular to constant function, so it cannot have it cannot have only one nodal domain. So we have exactly 2 nodal domains. So using Korang nodal domain theorem, McGrath obtained a symmetry of a first eigenfunction. He says if the first eigenvalue is less than 1, then and also the surface is invariant under the reflection through a plane, then first Steklov eigenfunction is invariant under the reflection. After this work, in 2020, or this is published in 2021, Lemma and Menendez observed two-piece property for free boundary minimal surface in a 3-ball. Actually, it should be embedded. So it says that if we have free boundary minimal surface which is embedded, then in a ball, then a coordinate plane which passes through the origin, a coordinate plane dissects the surface into 2 components. So using these results, Kussner and McGrath observed that each boundary component of the embedded free boundary minimal annulus in a ball should be convex on the sphere. It means if we consider a coordinate plane, then it should be meet a boundary component at most 2 points. So my approach is the finding a coordinate plane that does not meet the boundary of the surface. And also, with this plane, we can consider a plane perpendicular to this plane, and this plane should have at most 2 intersection points with each boundary component. So we have at most 2 intersection points with these boundary components, and at the same time we have at most 2 intersection points with these boundary components. Actually, it may not be a coordinate plane, but we have only perpendicular condition with our plane pi. So this observation comes from the following claim. It says if we have a convex closed curve on 2 spheres, then we can find an equatorial disk that does not meet the convex curve. And we can find this equatorial disk explicitly and explicitly. This equatorial disk is perpendicular to some vector, which is the integral of the position vector over the convex curve. Let's say this vector by a flux vector of C. Actually, the flux vector is very important concept in minimal surface theory. It is defined by the integral of the unique outward conormal vector along a boundary component of the minimal surface. Then since in our case is the free boundary minimal surface in the unit ball, so this unique conformal vector is identical to the position vector on a boundary component. So the two concepts is identical for our case. And since using minimality, the sum of flux vectors along the boundary components, all the boundary components should be 0, because since we have harmonicity of coordinate functions, so by Stokes' theorem, we have integral of the normal derivative of the position vector along the boundary should be 0. And by using boundary condition, this integrand should be the position vector. So the sum of flux vectors along the boundary components should be 0. So if we take an equatorial disk perpendicular to the flux vector of a boundary component, then this equatorial disk does not meet the boundary component by the claim, and also this equatorial disk does not meet the other boundary component. So we can show that the first observation in the previous slide. Actually, the existence of this equatorial disk that does not meet the given convex curve on sphere is well known by, and it is proved by integral geometry method. This claim gives constructive proof of that fact. So using previous observation, we can show the following lemma. So it says if the first eigenvalue is less than 1, then the first eigenfunction is sign changing in one boundary component, and in this boundary component there are exactly 2 nodal points. So let me give proofs of theorem 1 and 2. So if you consider a normalized flux vector along the boundary component and say small fi, then we know that the sum of small f1 and small f2 should be 0. And since the reflection symmetry, since we have a reflection symmetry of the surface, a boundary component, the reflection maps a boundary component into another boundary component, and it can be the given boundary component or the other boundary component. So the reflection maps small f1 into small f1 itself or small f2. So let's say f1 as E3 vector, and then the first case should be for the first case we may assume the reflection planes should be our reflection planes are x2 x3 plane or x1 x3 plane. And for the second case, the reflection plane should be the x1 x2 plane. And for for the second case, this plane does not meet the boundary component, so this case corresponds to theorem 2. So by using this lemma, we take a boundary component as in the lemma, and then the first eigenfunction is sign changing in this boundary component, and we have exactly 2 nodal points in this boundary component. So for the case 1, let's say the reflection planes by x1, pi 1 and pi 2, and that are defined by x1 is equal to 0 and x2 is equal to 0. So we can show that by the symmetry of the first eigenfunction, nodal points in our boundary component should lie on the reflection planes. If not, by symmetry of the first eigenfunction, we have 4 nodal points in this boundary component, which is contradiction to the previous lemma. So we have nodal points lie on one of our reflection planes. Then the symmetry of the first eigenfunction, we have P2 in a reflection plane, and there are no other nodal points in this boundary component. So U has fixed sign in this side, and also U has fixed sign in this side. In addition, we have the symmetry of the first eigenfunction. The 2 signs should be the same. So U is not sign changing in this boundary component. It is contradiction to our previous lemma. Now for the second case, let's say the reflection plane pi 1, which is defined by x3 coordinate is equal to 0. Then this plane does not meet the boundary of the surface. So since we have 2 nodal points in a boundary component, by the symmetry of the first eigenfunction, we have 2 nodal points in the other boundary component. Let's say P3 and P4. Then these 4 points lie in a plane which is perpendicular to pi 1, and and since our previous observation, this plane should meet the boundary only at these 4 points, P1, P2, P3, and P4. So we have fixed sign in this part and fixed sign in this part. And also by the symmetry of the first eigenfunction, we have fixed sign in this part and also fixed sign in this part. And since the first eigenfunction is perpendicular to constant function, so the integral of the first eigenfunction over the boundary, it should be 0. So this sign is different from this sign. Now let's say this plane by pi 2, which has a point whose x2 coordinate is C. Then the integral of the product of the first eigenfunction with x2 minus c over the boundary is non-zero. However, the first eigenfunction is perpendicular to constant function and coordinate functions, so this integral should be 0, which leads contradiction. Now, let me give other characterizations of the critical catenoid. Before to do that, let me introduce Bujoling uniqueness theorem. This theorem says if we have analytic curve in R3 and analytic normal vector field N such that the tangent vector of the curve is non-zero and the length of the normal vector should be 1 and the tangent vector is perpendicular to the given analytic normal field. And then we have minimal immersion phi such that it contains the analytic curve and whose Gauss map at this curve should be the given normal vector field. Using Bujoling uniqueness theorem, Kapolas and Lee obtained a uniqueness theorem for critical catenoid. They show that if you have a rotationally symmetric boundary component, then the surface should be the critical catenoid. Now let me give a proof. If you take an analytic curve along this boundary component and a normal vector field along this curve by the normalization of the outer product of the tangent vector and the position vector. So this is the Gauss map at the boundary point. And then since our boundary component is rotationally symmetric, it has reflection symmetry with respect to a plane that passing through the rotation axis. So let's say the reflection plane by pi. Then we have a boundary point P and a reflection point. Then since the tangent vector along the boundary at P maps to a tangent vector along the boundary at the reflection point. And also the conormal vector at P is the position vector. So it maps, the reflection maps the conormal vector at P to the conormal vector at the reflection point. Since the Gauss map is the perpendicular to the tangent vector and the conormal vector, so reflection maps the Gauss map at P to Gauss map at the reflection point. However, the direction could be reversed, but in our case, for minimal annulus case, we can show that the direction should be as in the picture. So we have this commutating relation. So by using Bujoling uniqueness theorem, we can show that we have a rotationally symmetric piece around C, and it coincides with our surface sigma. And also, we can show that by applying uniqueness theorem several times, we can show that the surface should be the congruent to the critical catenoid. So we can develop this argument for compact embedded free boundary minimal surface in three-dimensional pole. So we have a boundary symmetry that says if we have n boundary components, and also if we have an orthogonal matrix A that maps a boundary component into another boundary component, then we have the Gauss map image of at AP is equal to plus minus a composite Gauss map at P. And this sign is fixed for all points in the boundary component. And if we consider M by minimal annulus, then the sign should be plus. So using this boundary symmetry, we can show that symmetry principle that says the symmetry inherited from the boundary symmetry. So if an orthogonal matrix A maps a boundary component into another boundary component, then M is invariant under that symmetry A. So using symmetry principle, we can extend our previous theorems. First is that if the boundary is invariant under the reflection through two coordinate planes, then the surface should be congruent to the critical catenoid. And also, if a boundary component is invariant under the reflection through two coordinate planes, it should be congruent to the critical catenoid. So, and also by using a half-pole theorem and Kostner-Maclaurin result, we can obtain if either the antipodal map or the reflection through a plane maps a boundary component into the other boundary component, then the surface should be congruent to the critical catenoid. Actually, in here, we have two reflection coordinate planes in corollary 1, but we can reduce one more coordinate planes if you assume congruence assumption on the boundary components. So the last theorem says if the boundary consists of two congruent components and it is invariant under the reflection through one coordinate plane, then the surface should be congruent to the critical catenoid. So the proof is follows from an observation about congruence of a piece of the surface in the half ball and the piece of the surface in the other half ball, and this half ball can be obtained by small fi. So let me give a proof of the last theorem. So since the congruence condition on the boundary components, we have an orthogonal matrix A such that A maps a boundary component into the other boundary component. So if since we denote F1 by 0, 0, 1, so let's define sigma 1 as a part of sigma included in half ball induced from F1, and we can define sigma 2. Then by symmetry principle, A maps sigma 1 into sigma 2. So if you consider a Gauss map and A composite the Gauss map, then A composite Gauss map should be a Gauss map of the surface. And so A composite Gauss map has the same direction with Gauss map or reversed direction with the Gauss map. Since the boundary symmetry for the minimal annulus, the sign should be identical. So if you consider a point P in sigma in the equatorial disk, then by symmetric principle, we have AP should be contained in the equatorial disk, and Gauss map composite with A is equal to A composite with the Gauss map. So since A maps a boundary component into the other boundary component, and it is O3, so A is represented by composition with B and reflection symmetry with respect to x1, x2 plane, and B is O2. So we can divide two cases. So first case is that B is a rotation about x3 axis, and second case is a reflection through a plane passing through the x3 axis, which is a line passing through F1 and F2. So using case study, we can show that sigma should be congruent to the critical catenoid. So briefly, for example, if we consider case 1 with B is Z3, then from the previous relation, if you have a point in sigma and equatorial disk, then we have these 3 points. And also, if the Gauss map at this point has non-zero x3 coordinate, let's say positive, then by the relation between A and G, we have Gauss map at AP has reversed x3 coordinate, and then by this procedure we have these two directions. So it says that x3 coordinate of the Gauss map at P should be 0. That says the sigma meets equatorial disk perpendicularly. So it's the half-bore theorem says sigma should be congruent to the critical catenoid. So this is the end of my talk, and thank you for listening, and hope to see you in the Q&A session. Bye.